Hello everyone, today let's solve the problem number 153. Find minimum and rotated sorted array. So what the question states here, we have been given a rotated sorted array of unique elements. So let's come to the example. You can clearly see here, we have been given rotated sorted array nums with the unique elements, right? So we have to find the minimum elements and because of logarithmic n time, not minimum element, sorry, we have to find the minimum element and because of log n time, right? So we have to strictly, they have asked here, we have to write an algorithm that runs in because of logarithmic n time. Means whenever you hear because of logarithmic time, either I remember of binary search or I remember of this one, segment tree and Fenwick tree, as it is related to search and return the element. Usually you should remember binary search, right? So if you would have guessed that we'll be making use of the binary search, it's correct. We'll be going with the binary search basically. So let's come to the first example here. So here in this case, we have the array that is rotated thrice here, or that is rotated 3 times here. You can clearly see, one, we have the elements 1, 2, 3, 4 and 5. So this 5 is first rotated once. So this becomes 5, 1, 2, 3, 4, right? So next 4 is rotated here. Then 4 comes here. And 3 is rotated here. Then 3 comes first here. So this will be 3, 4, 5, 1, 2. Right? 3, 4, 5, 1, 2. So we have, this is already rotated thrice, this is sorted and rotated thrice. So we shouldn't, they have strictly said that this is already sorted and this one rotated. So we shouldn't sort this one and find the first element. That also we can do. This one we can do easily, right? If we do the sorting and if we give here nums of 0, we'll get the solution. Here in this case, the first element, nums of 0 is nothing but the first element, 0th index element, the element that is present at the index 0. So if we return it, we will get the solution. Sorting, we shouldn't go with the sorting. That is the reason they have asked us to write an algorithm that runs in big of logarithmic n time, right? So here we have to find the smallest element that is present in the array, right? Here in this case, looking at it, we can clearly say 1 is the smallest element. We have to return 1. So the output that we got here is 1. Same goes with example 2 as well. We have the array that is rotated 4 times. They have strictly mentioned here 4, 5, 6, 7. You can clearly see it starts from 0 here. Instead of here it started from 1, here it starts from 0. We have 0, 1, 2. So initially, so 0 is the smallest element. We need to return 0 in this case. Let's come to the third case here, or I mean third example here. So we have 11, 13, 15 and 17. So the original array was 11, 13, 15 and 17 itself, and it was rotated 4 times, right? So it was rotated 4 times. When you rotate this 4 times, same elements will come, right? 11, 13, 15, 17. You rotate this one first 4 times. Same solution we get, 11, 13, 15, 17 here, right? So the first element itself is the smallest element that is present in this array. So 11, among 11, 13, 15, 17, 11 is the smallest element, right? So we will return the smallest element. This one, 11 is the smallest element, right? So here in the output. So I hope this is clear. We discussed the examples clearly, right? So I hope the question is clear. I hope what we need to do is completely clear as well. They have mentioned wonderful examples just for the sake of understanding, right? So first what we'll do, let's discuss the approach, and then let's discuss the edge cases one by one, and then let's write the code and discuss the complexities for the code that we have written. Initially, as usual, let's discuss the approach first. Here, the first thing that we need to notice here is we will be going with the binary search. We have already discussed this one, as we need to write the algorithm n because of logarithmic n complexity. We'll be going with the binary search, right? So I have considered the first example that they have given in the question. We have already discussed this one, so that it will be easier to understand the approach, right? Step by step approach here in this case. So this is rotated 3 times, and the smallest element here in the array is 1. So we have returned 1 as output. So they have asked us to find the smallest element in the rotated sorted array, right? 1 is the smallest element, and we have to return this one in this case. Let's come to the step by step execution here. So first step here is we'll be going with the 2 pointers. One is left and right. So left, we have initialized this one to the first index or 0th index, and right, we have initialized this one to the last index or the 4th index accordingly with the example. See here, this is 0 indexed, right? 0, 1, 2, 3, 4. So we have initialized left pointer to this one and the right pointer to last index, left pointer to first index and right pointer to last index here in this case. Let's come to the step 1 here. Mid, we will give left plus right by 2 here in this case. Nothing but 0 plus 4 by 2 is nothing but 2 here. Mid is 2. Means 0, just give me a second here. 0, 1, 2, 3, 4 we have, right? So this one 2 is the mid element. So this one is mid element, the index 2 here in this case, right? So here 0 plus 4 by 2 here in this case, mid is 2. So nums of mid equals 5. So in this case, the element that we have here is 5, right? So nums of mid is 5. The index is 2. Index is 2. The element that is present in the index 2 is 5. Nums of mid is 5 in this case. Since nums of mid is greater than nums of right, nums of mid is greater than nums of right. Nums of right is nothing but here 2. So if this one nums of mid is greater than here, nums of left is 3, first element. Nums of left is 3, nums of mid is nothing but, we have found out that one 5, element 5, and nums of right is nothing but the last element, this one we are speaking of 2 here in this case, right? Since nums of mid, this is greater than nums of right. 5 is greater than 2 here in this case, right? So since nums of mid is greater than nums of right, we will move the left to mid plus 1. We will move the left to mid plus 1. When we move the left to mid plus 1, here we have got the, so we'll move this one left to mid plus 1 as mid is this one, second index. We will be moving this one to the third index, means the element 1. Now left is at mid plus 1, means now nums of left is 1. So mid plus 1 means next index, right? The element that is present at the third index is 1. Now we have nums of left is 1 here in this case. This is fine. So let's move on with the second step here. Mid, now if we want to calculate the mid, then it will be 3 plus 4 by 2, as nums of left is at 3. This will be 3 plus 4 by 2 if you want to calculate the mid. Then this is 3, third index, nothing but nums of mid, this one, nums of mid, nothing but the element present at the third index is, the value is 1. We already know this one, right? Since nums of mid, now nums of mid is 3, right? Nums of mid is 1, sorry. Nums of mid is 1, sorry, not the nums of mid, confused here. Just give me a second here. Just give me a second here. Yeah, here nums of mid is less than or equal to nums of right. Right? Nums of mid is less than or equal to nums of right. Sorry, I got confused here. So here now the nums of mid is 1. Right? Nums of mid, now it is 1. So in this case, now the nums of mid is 1. So 1 is less than or equal to 2. Right? 1 is less than or equal to 2. Means mid we are considering with this one, nums of right here in this case. Nums of right value is 2. So 1 is less than or equal to 2 here in this case. Nums of mid less than or equal to nums of right. So we will move the right to mid. We will move the right to mid as well. So here now this one, right is also at the index 3 and left is also at the index 3. Right? Now we will move the right to mid equals 3. Right? So left is also index 3, right is also at index 3. So we will, what we will do, since this one nums of mid is less than or equal to nums of right, we will return the value. Nums of left equals 1. Nums of left equals 1. We will return the value, or the final value we will return here, nums of left equals 1 in this case. Since why we are returning nums of left equals 1? Because nums of mid is less than or equal to nums of right here. In this case, pure binary search, right? So we are going with the pure binary search here, if you know the binary search pretty well. So here nums of left equals 1. This we will return this one as output. right? So this we will return as output. The value that we got here is 1, and the answer that they've given for the question 1 is also 1 here in this case. So this matches the output that they have given for the example 1. Our output matches with the output that they have given for the example 1 in the question. So the approach works absolutely correct in this case, right? So as we are familiar with the approach, let's discuss the edge cases one by one quickly, right? So first edge case here is already sorted. Here you can clearly see all the elements are sorted, right, in the ascending order here. So here output will be 1. Output will be 1 in this case. Why? The first element is the minimum as the array is sorted here, right? So let's move on with the second edge case here, rotated once here. So I can clearly see 1, 2, 3, 4, 5 are the elements we have. 5 came first here. This is array is rotated once. 5 came first here, right? So the output is quite obviously 1 here in this case, right? So minimum moves to the index 1 as this one. The array is rotated once here. Let's move on with the third edge case here, rotated at the last element. Rotated at the last element. Here also output is 1. So the array is rotated 4 times here. The last element is the minimum. So the last element is the minimum here in this case, right? So the output is 1 here in this case. Let's move on with the final edge case of the fourth edge case here. Fourth edge case here, single element. We have only one element, nothing but here nums of 100 we have considered the 100, right? So output will be quite obviously 100 itself. Because we have only one element, so we will return that itself, right? So we will be returning that itself. Here output will be 100 in this case. These are the 4 edge cases that we need to keep in mind. First edge case we discussed is already sorted. The second edge case that we discussed is rotated once. The third edge case we discussed is rotated last element. The fourth edge case that we discussed here is this one, single element. These are the 4 edge cases that we need to keep in mind, right? Now we are familiar with the approach as well as the edge cases. As we are familiar with the approach and edge cases, it will be easier to write the code. Now let's start writing the code. So let's start writing the code now. The first thing here is we have to initialize the left and right pointers, right? So I'll just go with here left equals 0, right equals 0. We are initializing left and right pointers with 0 initially. So next we have to continue the binary search. I'll just quickly make use of the while loop here. Left pointer has to be smaller than the right pointer always, right? So this is fine if you know the binary search. First thing is we have to find the middle index. So I'll just give here int mid equals. So this one left plus right minus left. Right minus left by 2. So we are just finding the middle index here. So if you remember the approach, we have to find the middle index. This is binary search, right? So we have to find the middle element. After finding the middle, middle index, what we need to do, if mid is greater than right, then min is in the right half. We saw this one in the example as well in the approach, right? The first example that we considered. If mid is greater than right, then min is in the right half. So mid was greater than right. 5 we got 5 was the element that was in the mid and 2 was in the right. If you remember, nums of it, mid was greater than right in our case. So that is the reason we considered the right half, right? So for that one we have to articulate that one in the form of code. Here nums of mid, if it is greater than nums of right here, this one, what we will do, we will go with left equals mid plus 1. We went with left equals mid plus 1 if you remember, right? The next index we considered, third index we considered in the in the approach. So else what we will do, if nums of mid is smaller than nums of right, then we'll go with right equals mid. So the next thing is we have to return the minimum element. Nothing but in our case, if you remember, we return nums of left, right? Always we need to return nums of left here. Nums of left will be this is fine. So even if it is nums of mid is smaller than nums of right, then what we will do, we will return the first element. We will consider the left half and we will return the first element. That itself will be the this one output or the minimum element. You can just check that, right? So we will be returning nums of left. This is this is it for the code. I have formatted the code. Let me hit the run button. So we are getting the wrong answer. Let's check what is wrong here. So here we are getting 3 as output instead of 1. We need to get 1, right, for the first one. So why we are getting 3 here in this case? The first element we are getting here. So yeah, what mistake I have done here is we have to initialize the right to last element, not the first, this one, right, first index. So here left we have initialized to the first index, nothing but the 0 here in this case initially. Right, we have to initialize this one to the last index, nothing but in this case length of the nums minus 1, the last index. So this is fine. This is the mistake I have done. I'll just run the code again. So now this has to work. Let's see. So yeah, you can clearly see here all the test cases, sample test cases are getting passed. So let me hit the submit button quickly. So I hope this works for all the test cases. Let's see. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct in this case, right? So let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is binary search on rotated sorted array, right? So, or we can just call this one as binary search, right? So what is the overall time complexity here? The time complexity, as we went with the binary search, the overall time complexity would be quite obviously because of logarithmic n, right? So the time complexity here is because of logarithmic n, because each step here reduces the search space by half. After finding the mid element, either we are going with the this one, so right half or the left half. So basically each step reduces the search space by half, right? So overall this one time complexity would be big of logarithmic n. So what will be the space complexity here? Overall space complexity would be big of 1 in this case. Why it is not big of n here? Because we are making use of only few variables in this case. We are making use of left and right. Also we are making use of mid here, this one. We are just making use of few variables, left, right and mid, which will lead us to the constant space complexity, nothing but big of 1 in this case. So the time complexity is big of logarithmic n, and the space complexity is big of 1 for the code that we have written, right? So I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching, guys.